So we have a distance versus time graph. That's the same as a displacement versus time or a position versus time. As long as whatever it is on the x-axis is measured in meters, that's like a position or a distance graph. When the object is at rest, that means it's staying in the same position or at the same distance. So it would be at rest in section B and in section D because it's not moving at all. Where it's changing speed is when it's curved, because your speed is just the slope of the position versus time graph. So here it starts pretty slow and then it gets steeper, meaning it's getting faster. So E was the section it was changing speed in. Moving forward means it's increasing graph, and at constant speed means it's straight. So A is moving forward at a constant speed. Backwards at a constant speed is C, because it's decreasing in its distance but still straight, so still constant. Another position versus time graph, we're calculating the total distance and total displacement. Right here, we just said the flat line staying at the same position is at rest, so it doesn't go any distance. From 30 down to -10, it's going down 40 meters. It's at rest again, and then it goes up another 10. Total distance, you add up all the different distances. 0, 40, 0, and 10 gives me a total distance of 50 meters. For displacement, we care just about the start and the finish. So you started at 30 meters and you ended at 0, so your position has changed by 30 meters and it's gone down or backwards 30 meters, so your displacement was -30. Instantaneous velocity at 5 seconds. At 5 seconds, we said it was at rest, so your velocity when you're at rest is 0. Instantaneous at 3.5 seconds, that's somewhere in here. Now, we do not know how to find velocity of a point, but we do know how to find velocity of a section, and this is at constant velocity, the whole section, so the velocity of this section is the velocity at that point. So velocity is V equals d over t. We have that it was 40 meters, and then we just look at how much time it took. We're not plugging in the 3.5. 3.5 is the time that like the clock reads. How much time that took is from 3 to 4 seconds, so 1 second. So 40 meters in 1 second is 40 meters per second. Technically it's negative because it's going backwards, but not a big deal. Now we are looking at a velocity versus time graph. So I like to think about this as the speedometer in your car. Speedometer. So imagine your speedometer starting at 0, going up to 4, staying there, going down to 2, staying there, and then going down to 0. So when it's at rest, is actually none of these sections. You could say point A and point F for those instants in time, but there's no actual interval, like any length of time that it stays at rest. I'm just going to say none, because you would need your velocity to be at 0 and stay at 0 for some length of time. When it's moving forward at a constant speed means constant velocity. Well, if your velocity is not changing, then your velocity graph should not be changing. So it's at constant speed in 2 sections, from B to C and from D to E. When it's speeding up, means your velocity is increasing, so your velocity is increasing from A to B. Again, thinking of your speedometer makes this easy. If your speedometer goes from 0 up to 4, you just got faster. If your speedometer stays at 4, you're just cruising at a constant speed. Moving backwards, you would need to have negative velocity. This is all positive velocities. It goes to a stop, but it never goes in the negative direction, so this was none. And the acceleration from C to D, well, I would use the VF equals VI plus AT from C to D in particular. Your final velocity was 2. The starting velocity was 4. Looking for A, and the time it took was from 4 to 6 is 2 seconds. Subtract the 4 over, you get -2 is A times 2. Divide the 2, you get A is -1. And the negative acceleration is just because it's slowing down, it's decreasing in speed. Remember, acceleration is the rate that the velocity changes, so it's how much velocity changed in the amount of time. So you also could use the A's delta V over T. It went from 4 to 2, so it lost 2 meters per second, and it took 2 seconds. So it's going to get you the exact same thing. It's basically the same equation, it's just rearranged. This is what's going to be given on your equation sheet, so this is probably your best bet if you don't want to memorize things. Roller coaster traveling with an initial speed of 15, deaccelerates uniformly at -7 meters per second squared. As soon as you see meters per second squared, that is not a velocity. That is the unit of acceleration. So you cannot put VF here. especially when it says it goes to a full stop. Your final velocity if you go to a stop has to be 0. And then we're looking for how far, so we're looking for distance here. So we're going to go up to our equations at the top and look for one that has VI, A, VF, and D, and it is the VF squared one. So VF squared equals VI squared plus 2AD. VF is 0, VI is 15 squared, 2 times negative 7D. 15 squared is 225. 2 times negative 7 times D is just minus 14D, and that equals 0. Can't combine these because D is a variable, they're not like terms, so I added the 14D over. So 14 distance is 225, and now we just divide the 14 over to cross off and get D by itself, and put that in your calculator, you get 16 meters. Number 9, a car accelerates from 4 meters per second to 12 meters per second. Meters per second tells me these are both velocities. Changing velocity because it's going from this one to 12. So I started at 4 and I ended at 12. That's my initial and my final. And then 8 seconds is my time. And we want to know how far it moved in that time. So we're looking for the distance. We have VI, VF, T, and looking for distance. So this one doesn't help you find distance. This is only for constant velocity, which is not the case. So we're between these two. But for both of these, you'll notice we still have something that we don't have. It's A. But we have no way to find A. So we can use this one to find the acceleration, and then you can use either one to find the distance. This is a two-part. At first, we're going to use the VF equals VI plus AT, which doesn't help me find distance, but it does help me find A, which I need. So 12 equals 4 plus A times 8. Subtract the 4 over, I get 8 equals A times 8, and then my acceleration is 1. How far did it move? So you can use either one of the equations that have distance in it. I use the D equals because it's already solved for distance. That means I don't have to do any rearranging. VI is 4 times time is 8 plus 1/2 acceleration 4 squared. Put it in your calculator and you should be getting 64 meters. A cat walks 4 meters east and a dog runs 8 meters west. Miles per hour, not meters. Their human walks at 5 miles per hour east, which of the following is incorrect. So with these relative velocities, it helps to draw a picture where they're all starting at the same spot, and then it's really easy to compare them to one another. So we have got a cat going 4 east, we've got a dog that's going 8 west, and we've got a human that's also going east, but it's going 5 miles per hour east, so it's a little bit faster than the cat. And drawing like the directions all starting the same and faster as longer is going to help us compare these to one another. And now we're just going through and seeing which one is not correct. Velocity of a cat relative to the dog is 12 east, so let's look at the cat compared to the dog, so we can ignore the human right now. So if the cat were to go 4 east and the dog were to go 8 miles west, then they would be 12 apart. And the cat is, if this is west and this is east, the cat is east of the dog. The dog is west and the cat is east, so this one was true, so we're going to cross it off. Velocity of the human relative to the cat, well, let's look. Human and the cat, they're both going east. If the human goes 5 east and the cat goes 4 east, then they're 1 apart, which is what it says. And it says that the human is east relative to the cat. So is the human east of the cat? Well, if you look just at these 2 dots, yes, the human is more on the east side, so it is east of the cat. So that was true. Cross that off. The dog relative to the human, so we're looking at these 2. The dog goes 8 this way, human goes 5 this way, then they are now 13 apart, which is what it says, 13 miles per hour apart relative to each other. And it says that the dog is east of the human, but the dog is over here. Compared to the human, the dog is very far west of the human, so that was incorrect. So C was our incorrect one, because that should have said west. And some of you might have said that D was the incorrect one, because it says velocity of the cat relative to the human. So cat relative to the human, we've already decided relative to one another, they're 1 apart. The cat is moving east, but just compared to the human, which is what I'm saying right here, ignoring which way the arrow is pointing, if you're looking just at these 2, the cat is on the west side of the human, so the cat would be 1 mile per hour west compared to the human. we're matching the distance versus time to a velocity versus time graph. Well, if this is a position versus time and it's going up and it's straight, this is constant velocity forward, or constant speed forward. So if I want to know what the velocity versus time graph looks like, well, constant velocity, the velocity graph should be constant. So that would be E, the last one, where it's staying at a constant rate. Your distance and your velocity graph should not be the same thing. They are different types of graphs. They should represent the same motion, but not in the same manner. This would be going forward at constant speed. This is also going at constant speed, but they should look different. Which of the following is the net force 0? Braking to a stop, definitely a net force there, because it's changing its velocity. Hitting a ball with a bat, not a hat. Definitely changing its velocity, applying a force. Moving at a constant speed is forces balanced. But A also says constant speed. The answer is just C. A would not be net force of 0 because if it's moving in a circular orbit, it has to have a force that makes it continue going in a circle. It has to have a force that's continuing it to turn. So think about if I were to like swing my keys in a circle, if the string broke, it doesn't just continue going in a circle on its own, it would fly off. It would need a force to continue going in a circle, so just the moving in a straight line at a constant speed is net force of 0, balanced forces. 30 Newton force required to accelerate a 2 kilogram object at an acceleration of 10, and we're looking for mu, the coefficient of friction, and this is like my applied force. So first things first, if you have your mass, you can find the force of gravity, because the force of gravity is just mass times 9.8. Here my mass is 2, so 2 times 9.8 gives me 19.6. And because it's on the floor, it's not falling down or accelerating up, so my normal force, how much the floor is pushing back, is also 19.6. And then it gave me that my applied force is 30 newtons. Now it didn't tell me any directions, so I just made the applied force go to the right. And the other thing that it gave me was my acceleration. If I have acceleration, I can plug into my F net equals ma. Mass of 2, acceleration is 10. That gives me that my net force is 20 newtons. So if I have a total or a net force of 20 and I have 30 this way, that means I must have an opposite force of friction of 10 newtons. And you can always double check. 30 minus 10, yeah, that gives me a net force of 20. And then last thing is I need to find the actual coefficient of friction. So the only equation with coefficient of friction is this. FF is mu Fn. FF we just said was 10, looking for mu. Fn we said was 19.6. We're going to divide. We need to divide the 19.6 over, not the 10, because we want to cross off and get mu all by itself. And that gives me mu is 0.51. So that would be my answer. Number 3, so an 85 kilogram crate is being pushed horizontally with a force of 80 newtons. We are given the coefficient of friction and we are looking for acceleration. So super similar to number 2, except for what we've been given and what we're finding are switched here. So I still have the mass, finding force of gravity the same way, 85 times 9.8. That gives me a force of gravity of 833. If it's on the ground or some surface, then the normal force would also be the same. And it's being pushed with a force of 800. And we've been given the mu. If you have the mu, then you can plug in and find the force of friction. So force of friction is mu, 0.2 times Fn, 833, and that gives me a friction force of 166.6. And drawing the diagram helps a ton on these. So on the midterm, when it is super important, just take the time to draw the diagram and don't make silly mistakes on it, especially in questions you know how to do. Last thing is asking for the acceleration. In order to find the acceleration, I need to find the net force so that I can plug into the only equation we have for the acceleration using forces. To find the net force, that's the total up and down. These are going to completely cancel out. And then 800 with 166 the other way, I would subtract them. So you get 800 minus 166.6 gives me my net force is 633.4. And now you just plug in. 633.4 equals my mass, 85A. I'm trying to get A by itself, so I divide the 85 over. That gives me an acceleration of 7.45. Ito is pulling a 5 kilogram sled through the snow at constant velocity using a horizontal force of 10. What is the coefficient of friction? I have the mass, so I can find the force of gravity or the weight in the normal, because mass times 9.8, 5 times 9.8 gives me 49 for both of those. Now I haven't been given any other number, so I can't do mu of n to find the force of friction, and I don't have the acceleration, but I do have that it's at a constant velocity. If it's at a constant velocity, that means your forces are balanced, your net force is 0, so the force of friction has to be the same as this applied force right here because they're balanced. My force of friction is just 10. And then asking for a coefficient, plug into the only equation with coefficient, mu of n. F of friction is 10, mu is what I'm looking for, normal force we just found was 49. Divide 49 over, because we're trying to cross off things to get mu by itself, and that's going to give me 0.2. I've got a 5 kilogram block, it's accelerating at 6, so I've got mass and acceleration, and we've got the applied force is 50. What is the coefficient of friction? Well, if you have the acceleration, then you can find the net force. So mass times acceleration, 5 times 6, gives me a net force of 30. Now you just look, this one already has the diagram partially done for us. So I have 50 newtons to the right, and if my net force is only 30, then I must have a friction force of 20 newtons, because 50 minus 20 would give me a total of 30. Now to find the force of friction, or the coefficient of friction, I would plug into this equation, which means I need to know my normal force. Well, finding normal is easy, you just find the weight. Mass times 9.8, that's the same as above, 49, and then this normal force would be 49. So I can plug in force of friction we just said was 20, mu, normal force we just said was 49. Divide over, and you get your mu is 0.408. If your forces are balanced, your net force is equal. If your net force is 0, it's in equilibrium. That means the object could either be at rest, right, not moving at all, or, and this is probably more common, at a constant velocity. So totally it could have completely balanced forces and still be moving to the right or to the left. As long as that is at a constant velocity, that doesn't mean there's a bigger force to the right or to the left. It means that they have to be balanced. The net force on an object that's moving at a constant velocity would be 0 because there's no acceleration. That means that they are balanced. Pretty much this question, but just trying to hammer that. A net force F acts on a mass m, causing it to accelerate at 4. If the same force acts on a mass of 2m, so now we are increasing the mass, so if it's more mass, that means it's heavier. If I have the same force on something that's heavier, would it go faster or slower? Hopefully you said slower, so we can cross off these, and it was twice the mass, so it should be half as slow. If it was 4, half of that would just be 2. So you can imagine you've got m with some force, now you've got 2m with that same force. This is definitely going to go slower because the same force on a heavier object would be slower. And it's a factor of 2, so a factor of 2 small. 4 kilogram stone attached to a string. It's moving at a constant speed of 4 and a radius of 0.8 centripetal acceleration. Centripetal acceleration is this AC, which is just v squared over r. We do not need the we do need the radius. We do not need the mass in this case because I just want the acceleration, not the force. So you're just plugging in 4 squared over 0.8, and that gives me an acceleration of 20. Object travels in a circular orbit. If the speed is tripled, its centripetal acceleration will be, well, if you look at your equation, v squared over r, if it's going faster, then it definitely has more acceleration because this is a direct relationship, right? More velocity does mean more acceleration, so we can cross off a and b. What you'll notice is that the velocity gets squared. So if I triple this velocity right here, that's really a factor of 9 times bigger because the v gets squared. If there was no squared there, then yeah, tripling the velocity is tripling the acceleration, but the velocity gets squared, so that's really like 9 v squared over r, which means 9 times the original acceleration. 3, which arrow shows the centripetal acceleration at the point shown? Well, centripetal acceleration goes to the center, so to the center in this case is to the left, so 1. And the velocity, so the velocity is the one that doesn't point to the center, velocity is which way it's moving at that point. So this one is going around in a clockwise motion. So at this point, it's moving directly down. So this would be my velocity, number 3, and then you'll notice that these two always make a right angle. Merry-go-round worker stands on the ride's platform this far from the center, so that makes it the radius. This is the centripetal acceleration, pulling her towards the center, and we are looking for the speed of the ride, the velocity. Well, centripetal acceleration is v squared over r. A, or the centripetal acceleration, is 2.67. V squared, I don't know, and then r is 6.3. To solve for v, first thing we need to get rid of is the 6.3, so I'm going to multiply that up because I want to cross it off. So multiply that up. So that gives me v squared is equal to, can't do that one in my head, 16.821. And then that's what the velocity squared is. I want just the velocity, so we're going to take the square root to undo v, and that gives me 4.1 meter per second. If an object O is moving in uniform circular motion around point P at a constant speed, which shows the centripetal force. Centripetal force goes to the center, acceleration and force both point to the center. Velocity is on the outside, which way it's moving. So the one that points to the center is 2. Projectile motion. So we have these equations. These are like our y equations because only the y component has acceleration. This one is for x only. So don't try and use this with any of your y values. And then for projectile motion, meaning anything that's like falling through the air, your acceleration will always be 9.8. A cannon fires a shell at an angle, which of the following is the same throughout. So if I have to throw something up like this, it's going to go up and down. The horizontal meaning x component of the velocity, well, yes, the x component of the velocity is constant because there's no acceleration sideways. So that's true. Its acceleration, its acceleration is negative 9.8 the entire time. It's not going to change, right? Gravity doesn't get stronger or weaker as the ball goes up or down a couple feet. And the vertical component of the velocity, that one would not stay constant. If you think about the vertical, meaning the y part, at first it starts going up, and then it's 0 at the top, and then it's going down. And even on its way up and on its way down, it's changing speed. So the only ones that are staying constant are both A and B. An arrow A is shot horizontally from a bow at a speed of 50 meters per second, and the second one is dropped at the same time from the same height. We're neglecting air friction, so we don't worry about it. Compared to the time it takes A to fall down, the time it takes B would be the exact same. So this is like that video I showed you with the ball that rolls off the table and the ball that's just dropped. They're going to hit at the same amount of time because the y component determines the time in the air. Determines time, not determine times. Y component determines time. If they're both going at the same height and they have the same y initial velocity, which is none in this case, then they're going to hit at the same time. What was different about A is it was going super fast to the side, but going fast horizontally doesn't make it fall down any faster. A baseball player throws a ball horizontally, which of the following describes the motion after it's thrown. Its vertical speed remains the same? Definitely not. If you throw something horizontally, its vertical motion at the very beginning, its VI for Y is going to be 0 because it only has a VX. It's thrown sideways. But that quickly changes. As soon as it's left from the hand, it's going to start falling down. So the vertical speed would not remain the same. It's going to accelerate down at a rate of negative 9.8 meters per second squared. Its horizontal speed would remain the same because the x velocity is constant. X velocity remains the same, yes, it's constant. Y velocity increases, yeah, it's accelerating. A golf club hits a golf ball so that it flies off with an initial velocity of 40 meters per second at an angle of 60 degrees. How high will the golf ball go? So we need to make our chart. First thing we need to do is find the initial x and y velocity. So VIX, oh no, I didn't write it on this. Is VIX is VI cosine of the angle. This will be given to you. So then VI is 40, and then cosine angle was 60. So you just type it exactly like this. Just make sure it's in degree mode, and that's going to give me that the x initial velocity is 20. So VIX is 20. VIY set up the same way, but it's VI sine. So 40 sine of 60, and that one gives me 34.64. 34.64 is my VI for Y. And then once you've taken your initial velocity and broken it down into the angles, now we don't need these anymore. The purpose was purely to break it down into the x and y components, and that's what I'll use from now on. Now, in a projectile motion, so anything flying through the air, your acceleration for the y component is always negative 9.8. Because this is something that was shot up at an angle, we know that at the very top, your y velocity is going, or v final, is going to be 0 at the top. So if I have the initial velocity for y, the acceleration, and the final velocity at the top, I can find the time, because I can use my VF equals VI plus AT. VF is 0. Make sure if you're plugging into an equation with 9.8, you use only y values, because these are totally separate, so my VI has to be the 34.64. And then plus negative 9.8t, subtract over, equals negative 9.8t, divide the negative 9.8. And that's going to give me my time is 3.53. Now that's the time it takes for the y velocity to go to 0, which is the time it takes to go to the top, so I'm going to call that t up. And then we're looking for how high the golf ball will go. Well, that's a distance. How high is technically the y distance. So now we're going to use y values. We have time now, so we have VIA, VF, and time. You can use either the VF squared or the D equals VIT. I prefer the D equals VIT equation because it's already solved for distance. So now we're just plugging in our initial velocity, and it has to be the y initial velocity times the time in the air plus 1/2, and you have to put the negative sign here, otherwise you get a much bigger number. And then you put it into your calculator and you should be getting 61.39 meters. If you're wondering, why did I use T up and not use T total? Well, I'm asking how high the ball will go. The very, very top is halfway through the flight at the top, the T up. I'm not going to ask the height right here. That would be T total. So you're going to use the T up. A golf club, it hits a ball so that, oh, it's the same one, right? 30 meters per second. No, never mind. So we're going to have to find our VIX and VIY again. 30 meters per second is VI. 40 is our angle. So we have 30 times cosine of 40. And VIY is 30 times sine of 40. Plug those into your calculator, and that gives me an initial velocity. Don't know that one off the top of my head. 22.98. And VIY, I got 19.28. And then we can always put acceleration as negative 9.8 because it's flying through the air. And again, it is an object that is being thrown up. So at the top, we can say that VF equals 0, or the y velocity goes to 0 at the top. We're looking for how far the ball will go horizontally before it lands. So that means I'm looking for my x distance. Well, x is easy. I can use v equals d over t. I have the x velocity. I need to find time. I can't use x to find time because I don't know the x distance, but I have enough information for y to find time. Because I have VI, A, and VF, I can use the VF equals VI plus AT. 0 equals 19.28 minus 9.8t. Subtract over. Equals. Divide the negative 9.8. On both sides. That gives me my time is 1.97. And again, that's the time it takes for the y velocity to go to 0. That's the time it takes to go to the top, so we'll call it t up. That's a 1, by the way. When we are looking to find the x distance, you don't want to use just the time it takes to go here. You want the total time it's in the air. And to go from t up to t total, well, this is symmetric, so you just double the time. So t total is twice that, 3.94 seconds. And then looking for x distance, now that we have time, we're ready. X velocity we have, and the x equation is going to be v equals t over t because x is constant, there is no acceleration. So plug in 22.98 equals distance over the total time in the air. To get distance by itself, you're going to multiply both sides by 3.94 to cross it off. And then multiply these and you get, for x distance, I got 90.44. Describe the vertical, horizontal, and velocities and acceleration at the point shown. Sorry, I wrote all over this. I'll just redot right here. At the very, very top, your vertical velocity, your Vy is 0. Your horizontal velocity is the same as what it started with. because your x velocity is constant, whatever it was at the beginning, that's your horizontal velocity at the top, and then your acceleration at that point is still negative 9.8. Your acceleration, or gravity, doesn't turn off when it gets to the top. It's still there, which is why a second later it's on its way down and getting faster and faster. A ball is thrown and shown, or follows this path as shown. Air resistance is negligible, meaning we can ignore air resistance. These two are at the same height above the ground, and we want to know how their speeds compare. We're not worried about signs, so yes, P is going up and R is going down. We're just comparing about which one is faster or slower. So think about when you shoot something up in the air, on its way up, its y velocity is getting slower and slower until its y velocity is 0 right here. And then on its way down, it gets faster and faster, and we know that these are completely symmetric. So if these two are at the same height, which is what it tells us, then these have to be equal to each other. And then our x velocity, we kind of ignore the x velocity, but that's okay because it's constant the whole time, so it's not going to affect which one's faster or slower. At the top, my y velocity is 0, I only have the x, so this one is definitely going to be slower. So I know P and R are equal to each other, and Q is going to be slower, so your answer was D. Q is less than P and R, which are equal to one another. A soccer ball is kicked horizontally off the top of a 22-meter high building, and it lands a distance 50 meters away. Find the initial horizontal velocity. So we're looking for this x velocity right here. So first things first, I have two distances. The x distance is 50 because that's horizontally on the ground. Up and down, the vertical or the y distance is negative 22 because it's falling down 22 meters. And then we can put acceleration in, and we are looking for the x velocity. First thing we need to find is time, because then I can just do v equals c over t. So I would need to use y variables to help me find my time. So, because this is thrown horizontally, a lot of people are tempted to use the VF equals 0 at the top, but if you look, it's starting at the top. So yes, your y velocity is 0 at the top, so I do have a y velocity 0, but it's not final. It's at the beginning, so it's the initial velocity that's 0. You also can think about if it's being shot out horizontally, then it's not shot up and down. So its initial velocity in the y direction, the up and down direction, is 0. And then we said we would use this to find time, so we can plug into v equals d over t. Distance a, initial velocity and time, we would use our d equals vit plus 1/2 at squared equation. Distance is negative 22, vi is 0, 1/2 negative 9.8 t squared. 0t goes away, half of negative 9.8 is negative 4.9. Let's divide both sides by the negative 4.9, and 4.49 equals t squared. That's what the time squared is. I want the time that's in the air, so you take the square root and you get that your time is 2.11 seconds. This is not a t up or a t total, it's just falling down, so it's just the time it takes to fall down. I don't need to worry about doubling it because it's not going up and down, so don't worry about labeling what type of time it is just the time. And then we said we were looking for the x distance. X equation is always v equals d over t, and we have the x distance is 50, and we have the time is 2.11. So put it in your calculator and you get 17. You get like 16.5 something, so then that rounds up to 17. These comparison ones, which one has a farther range? Remember, range is talking about the x distance. So for this one, you can look at the angle. You also need to notice, like, oh, they're shot off at different velocities. So let's look at the different components, because the y velocities and the x component of the velocity are what's really going to tell me these things right here. So farther range, well, you'll notice that they both have the same y velocity, and then B has a greater x velocity. So if they have the same y, and this one has a greater x velocity, then this one's going to go faster, or not fast, well, yes, faster, but also farther in the x direction, so B. Which one reaches the higher maximum height? Well, that just matters which one was thrown up with the most up velocity. If you look at their y components, they have the same y velocity, so it would be the same for both. Which one's the air longer? Time, we just wrote on the other page, time is determined by the y component. So again, looking at our y velocities, they both have 40, so they're going to be in the air for the same amount of time. which is why earlier I said, oh, a bigger x velocity, that means it goes farther, because they were in the air for the same amount of time. Which one hits the ground with a faster velocity? So that's not talking about x or specifically y velocity, it's talking about the total or the both of them together velocity. So I'm going to look at what they went up with, because if this one goes up with 50, then it's going to come down with 50. If this one went up with 57, then it's going to come down with 57. So the one that hits the ground with a faster velocity is the one that went up with a faster velocity, B. Number 10, we've got two horizontal projectiles off of different height tables. Which one hits the ground first? Well, time is determined by the y. They have different y's, so the one that will have the less time in the air hit the ground first would be the one with the less height to fall, B. Which one lands with slower velocity? Well, they both start with different x velocities, and this one's going to fall down less distance, so it'll have less y velocity. So B for two reasons, because it has less x velocity than A, and because when it hits the ground, it'll have less vertical velocity than A. And which one lands closest to the table? Well, the one that's going slower and spends less time in the air, B. A ball is thrown at an angle of 38. What happens to the magnitude of the ball's vertical acceleration during the total time it's in the air? So vertical is talking about your y. Well, your y acceleration is negative 9.8. There's no point in the ball's path that gravity turned off or got weaker or stronger, so it's negative 9.8 the whole time, so it stays the same. Momentum. So a gun backfires when a bullet is fired. The total momentum, so it doesn't matter what the system or what the situation is, your total momentum has to be conserved so it stays the same. Again, talking about a gun backfiring when the bullet is fired. I guess the bullet goes this way and this is the gun backfiring. The momentum of the gun, we're seeing how that compares to the momentum of the bullet. Well, we said the total momentum has to stay the same. Before the gun is fired, the total momentum is 0. So after the gun is fired, even though these are moving really, really fast and apart, your total momentum still has to be 0. The only way you can have a total of 0 and have two objects moving is if they completely cancel one another out. Well, they can only cancel each other out if they're the same, right? You can't have the bullet having a momentum of 100 and then the gun having a momentum of 10. That doesn't cancel out to 0. It has to be 100, 100. Now, they don't go at the same velocity because they have different masses. So the one that has a much smaller mass goes much faster, and the one that has a much bigger mass goes much slower, but they still have the same momentum. Remember, momentum is mass times the velocity, so you can have a big momentum with a small mass if you have a big velocity, and vice versa. We've got a 20 kilogram car moving at 3 meters per second, and it's stopped by a constant force of 15. Stop meaning Vf is equal to 0. We're looking for the impulse, so impulse is F delta T. I do have F, but I don't have T, but impulse is also equal to M delta V. So let's just use this side because I do have mass and the velocities. So 20 times V final minus V initial would be 0 minus 3. So that's going to give me 20 times negative 3 or negative 60. What is the change in momentum? Well, impulse and change in momentum are the same thing, so I just found the change in momentum, negative 60. And we want to know how much time or how many seconds the force must act to stop it, so we'll use the F delta T equals M delta V. Force is 15, looking for the change in time. You can plug in 20 times 0 minus 3 again, or we just said it was negative 60. Divide the 15 over, and then you get your time is 4 seconds, I think. You should not be getting a negative time. I should have put a negative sign on this force because if it's stopping, the force should be negative, so that was my bad. But you do get the right number. Number 6, we've got an unbalanced force of 20 newtons applied to an object for 10 seconds. The change in momentum, well, change in momentum is M delta V. Don't have either one of those, but it's equal to the F delta T, so you can just do 20 times 10 seconds and get the change in momentum is 200. Two carts of mass 5 and 1 are initially at rest. 5 cart then is pressed, I don't know, there's some spring, pushes them apart, goes westward, that's left, so I'm going to make that a negative 2, and finding the velocity of the 1 kilogram cart. Well, before we do any math, because they were both at rest and then they were sprung apart, total momentum was 0, and it has to stay conserved. So just like we were saying with the gun, these two have to have the same momentum going off. So that means that the heavier one will go slower and the lighter one, the 1 kilogram, will go faster. So we can cross off A automatically without plugging into any equation. Now we're going to plug into our conservation of momentum equation. And the left side becomes really easy because they were at rest at first, so that just becomes 0. And then the right side, we have 5 times the negative 2 plus 1 times we don't know their velocity. So that's just negative 10 plus 1v. Add the 10 over, so then your velocity is 10, which we said it was going to be faster. In this case, it had 1/5 the mass, so it was 5 times faster. And it's in the opposite direction because they cancel out. Momentums, not velocities. Oh, explain why this velocity is more, because this one has less mass with the same momentum. So it has to go faster. If it has less mass, it has to make up with faster velocity to have the same momentum as this guy. A 2 kilogram ball is traveling north at 4 meters per second when it collides with a 1.5 kilogram ball traveling south, meaning in the negative direction at 8. Make sure you put a negative there. What is the total momentum? So find the momentum of each. This would have a momentum of 8, and this one has a momentum of negative 4. No. Yes. And then, did I do it? That's not right. Wait. 1.8 times 8 is definitely not 4. Or 1.5 times, yes, this is negative 12. So then you have negative 12 and 8. To find the total, you would just add them. You get your total momentum is 4, negative 4, and that just means south. My bad, sorry, I just looked at my answer and not the step in between. So you have momentum of 8 upwards and 12 downwards, so that's 8 plus negative 12, which gives me negative 4. So my total is 4, negative, just saying it's in the negative direction or south. If my mass doubles and my velocity halves, what will the momentum do? So P equals mv. If I have twice the mass and 1/2 the velocity, well, doubling and halving cancel each other out, so it actually stays the exact same. A 2 kilogram blob of putty is moving at 4 meters per second. Lands into a 6 kilogram at rest. They stick together, and what is the speed of them stuck together? So that would be 2 times 4 plus 6 is at rest, so equals, or times 0 equals 2. Now these two are stuck together, so they share the same velocity, so it's just 2v plus 6v. And again, they're stuck together, so this is the same velocity, so I combine those like terms to be 8v. 6 times 0 is just 0, so I have 8 equals 8v, meaning the velocity when they stick together is 1. Now a quick check, we knew that when this one hit the one at rest and they went off together, we knew it had to be slower, so you knew your answer was at least less than 4, so 1 at least is reasonable. In the above problem, which of the following is false? The 2 kilograms momentum decreased. Well, we just said when this one hits, it would slow down, so its momentum would decrease, so that's true. 6 kilograms increased. Well, it was at rest and now it's moving, so definitely increased momentum because it increased in speed. The total momentum was unchanged. That's always true. Total momentum stays the same. It's conserved. The 2 kilograms momentum was unchanged. So that is false because the 2 kilogram lost momentum because it went from a velocity of 4 to what? Slow down. 2 cars with the same speed, which has more momentum? The one that has more mass. 2 cars with the same mass, which has more momentum, the one that has more speed. Now you can only say more mass means more momentum if they're going at the same speed, and you can only say more speed means more momentum if they're at the same mass. For example, if we go back to number 7, the 5 kilogram had more mass than the 1 kilogram, but they had the same momentum because this one went slower and this one went faster. So careful, the other thing has to be the same to say more mass or more speed means more momentum. And energy. As the pendulum swings from position A to position B, we're looking for what happens to the potential, the kinetic, and the total energy. So let's start with potential because that's the easiest one. Potential energy depends on the height. So as you're going from A to B, it's increasing in height, so its potential must increase. Your total, no matter what, is staying the same. So if your potential is increasing but the total stays the same, that means you must decrease kinetic. Which makes sense because as it swings up, it's getting slower. So just finding the one that agrees with these 3. You get C, kinetic energy decreases, yes, and total energy remains constant, yep. 300 kilogram roller coaster starts from rest at the top of a 20 meter hill. What is the speed at a 5 meter hill later on? So it helps to draw a picture. We've got 20 meter high and 5 meter high, and we need to find the potential and the kinetic at both spots because we need to be able to compare total energies. So I have the mass and I have two heights. This is the starting height, so I'm just going to plug into my PE is mgh equation. Mass is 300, G is 9.8, starting height was 20. That gives me a potential energy of 58,800. And then it says it starts from rest, so if your velocity is 0, your kinetic energy is 0, and that was only at the top that it started from rest. Now I'm looking at 5 meter high hill, so plug into mgh. That is going to give me a kinetic energy of potential energy of 14,700. Now I need to know the kinetic energy in order to find the velocity at that point, because then I can just plug into the 1/2 mv squared equation. In order to find the kinetic energy, well, we know the total energy of the system is conserved, so let's go back to the beginning. The total energy that I started with was the 58,800. So if that's my total energy, at this point I only have 14,700 potential, then you can just find your missing kinetic by subtracting. So take your total, subtract the potential energy, and that gives me my missing kinetic, which was then 44,100. And now I can plug into my kinetic energy equals 1/2 mass of 300 v squared to get my velocity at that point. Half of 300 is 150. 44,100, divide the 150 over, take the square, or first get the number, 294 is v squared, that's velocity squared, take the square root, you get your velocity is 17.14 meters per second. We have a graph of the potential energy, at which point is the object at rest. So object at rest is when your kinetic energy is 0. So that means you have the least kinetic energy, which means that you have the most potential energy. Because the total stays the same, kinetic and potential always are like opposites or inverses of each other. So where you have the most potential energy is this point at the biggest potential energy graph, so that was point A. Where it's moving the fastest is where you have the most kinetic, which means you have the least potential. So you just go to the graph. The potential was least at point C. You also can think about if your potential graph looks like this, then your kinetic graph would look like this, the complete opposite. So the least kinetic was A, and the most or the fastest, most kinetic or the fastest would be point C at the end. Skier starts from rest at the top of a mountain, and when he reaches the bottom, he has a velocity of 25. How tall is the mountain? So we're looking for this height right here. You'll notice that we do not have the mass, which is okay. We'll just use m. We do have velocity, so we can plug into 1/2 mv squared. Again, don't have mass, so let's just use the letter m. 25 squared, and then half it gives me 312.5 m. So I'm going to go at the bottom. My kinetic energy is 312.5 m, and my potential energy at the bottom is 0, because the height would be 0 on the ground. Now we go up to the top. It started from rest, and my kinetic energy is 0 at the top. And if the total energy is staying the same, because energy is conserved, that means that the potential energy I started with had to be the 312.5 m. And we are looking for how tall the mountain is or how high it is. Well, potential energy is mass times gravity times the height. So if I know my potential energy is 312.5 m, and this equals m times gravity 9.8 times height, to get h by itself, we're going to divide by m. Oh look, the m's cancel, which is what we wanted to happen. And then divide the 9.8 over as well, and that gives me a height of 31.989 meters. I'm going to leave the meters off so you don't think that that's a mass. So in this case, we didn't have the mass. It's okay because it ended up canceling out in the end, so we just used the letter m for mass. 15 kilogram roller coaster starts from rest, meaning kinetic is 0 at point A. When it reaches point C at a height of 25, it has a velocity of 10, meaning it has both potential and kinetic energy here. And because I have both the height and the velocity, I can actually plug in and find those. So potential is mgh. 15, 9.8 times 25 gives me a potential energy of 3,675. And then kinetic is 1/2 mv squared. 1/2, 15, 10 squared gives me a kinetic energy of 750. And I want to know what the height is here, meaning I need to know the potential at point A. Well, we know total energy is conserved, so in this case, we're using this point to find our total energy because we know both energies here. Normally use the first point, but this is where the information is. So to find the total energy, you just add them together. That gives me a total energy of 4,425. And if at point A I have 0 kinetic, that means my potential has to be the 4,425. Still not done because I asked how high is point A, so I'm going to plug into my PE is mgh. Potential energy is 4425, mass is 15, G is 9.8 times height. This multiplies, you get 147 height, and then last step is to divide the 147 over, and that gives me a height of 30.1 meters. And it had to be higher than 25, because otherwise that wouldn't make sense. Because it got faster. Okay, steady heart, guys.